Good morning to everybody. We're going to jump right back in where we were. I think we're making good progress. Anybody have any questions before we get started? All right. I think what we'll do today, we'll do some more hybridization. We'll do some more formal charge. I think we're doing 169 the other day. And we'll do, I want to go up and work on some of these problems where you have to convert from skeletal to line and Lewis, and then from condensed to Lewis. I want to do that real quick. I sent a video for that like early, but we haven't really touched it. So I want to talk about that too today. But let's go back to, I want to start right here at 170. And let me cut it and put it on another paper, another page.
The problems that we need to work, are they going to be the ones that you have had highlighted?
Yeah, the one, and we're not doing we don't have time in every single one of these. So the ones that we pick out, those are the ones we're working, and those will be the ones you turn in.
Okay.
Yeah, great question.
And then, like, for instance, like 169, when we did that one the other day, we just did A, C, E, and G. Would we finish B, D, and F? Or we...
Right.
Okay.
Yeah, so those A, C, and G, when you turn this in, that's what you're responsible for, unless I say you need to finish blah, blah, blah.
Okay.
Right.
Thank you.
Good question. And thanks for asking it now and not a month from now. That's good. Let me put the date in. All right. So we're still talking about hybridization. And then we're going to transition and start talking about these different structures. And then we're going to move on to, because we already talked about bonding. We just haven't talked about the different types, polar covalent, non-polar covalent, so on and so forth. So we're going to move on and talk about that as well. But let's do this question right quick. Actually, let's do 170 and the one underneath it, 171. That's a good question too. And can somebody tell me while I'm doing this, can somebody tell me when you make a bond between a covalent bond between atoms, what are you actually doing? Like, what's happening in that process? If you're making a covalent bond, what has to happen?
Its orbitals are overlapping one another.
Orbital overlap. Very good. You have to have orbital overlap in order for a bond to form. That's exactly right. Thank you for that. All right, so let's go up here, and that's what these questions are asking. When it says what orbitals are formed or used to form each indicated bond, you need to know the hybridization state of the atoms so you'll know what orbitals are overlapping. That's what it's asking. All right, so let's do A. Let's start out with something simple. We'll start out with A. And if you look at A, the arrow is pointing here. Right, so it's looking at those two carbons. And this is why I want to go and talk about skeletal forms and line forms and Lewis forms, because I don't want you to get confused. When you see a structure like A, that's really a 6-membered ring with 6 carbons. Bound like so, right? And then each one of those carbons has 2 hydrogens on it. Even though in the skeletal form, you don't have to show that, but it's there, the hydrogens are there. All right. So if you look at the carbon in A, there are 2 hydrogens on each one of those carbons. Right. This is what we call a skeletal form, where you don't have to show the atoms. Where you don't have to show the carbons. If there's another atom like oxygen or nitrogen or something like that, you do have to show that. All right. So the question is, what is the hybridization state of those 2 carbons? If they have 4 groups to them, all sigma bonds, both of them, what is the hybridization? Speak up, I can hear you.
Is it SP3?
SP3, very good. So it's SP3 for both of them, yeah?
Yes.
Okay, so back to the question. What orbitals are used to form each individual bond? So for that sigma bond between those 2 carbons, what's overlapping to make those sigma bonds? That one sigma bond between those 2 carbons.
The p orbitals?
If it was P, it would be a pi bond, right?
Yes.
Remember, your sigma bonds come from hybridized orbital overlap, and your pi bonds come from unhybridized p orbital overlap. So this bond is the result of sp3 overlap,
Oh, okay, okay.
right? Right, that's that for that bond.
Can you explain that again, please?
Yeah, so both carbons are sp3 hybridized. Do you agree with that?
Yes.
Okay, and then the sigma bond between them, because they're both sp3 hybridized, must be the result of sp3 overlap. Because remember, for sp3 hybridized carbon, it has 4 hybrids around it, 4 sp3 hybrids around it. Is that right?
Yes.
Mm-hmm. So in order for it to form a bond with another carbon that's sp3 hybridized, those are the hybrids that overlap. Right. Did that answer it, or?
Yes.
Okay, all right, good. Good question. All right, let's do the top. There's a CH bond up here. All right. The carbon is, what do you think? What's the hybridization state? Right, you don't see any pi bonds anywhere in this molecule. So every carbon in here is going to have the same hybridization state. Which is what?
SP3.
sp3, good. So that carbon is sp3. And then the hydrogen, it's a 1s orbital with 1 electron, right? So it can't hybridize because it doesn't have any orbitals to mix with. So the hydrogen itself is just s, right? It's just an s orbital, right? So what overlap is happening there?
SP3S.
Good, sp3 s overlap. Sorry about that. sp3 s overlap. Very good. Any question about anybody not seeing that? Say something. Don't get lost in the sauce. Go ahead.
So it's sp3s overlap because the hydrogen has 1 unhybridized s orbital.
Yeah, it's just a s orbital. Because remember, hydrogen has 1 electron, right? It's group 1, all the way over to the far left of the periodic table. So it can't hybridize because it's just one S1. That's the electron configuration for it. Is that right? Are you following that?
Yes.
Okay. All right. Let's go to the next one. Let's do B. We'll do all three of these. Let's do this one first, though. Right? So that carbon, you got a carbon here and a carbon here. What's the hybridization state of the, let me change the color on that. The blue carbon at the bottom.
SP3.
Good, that's sp3. Excellent. What about the top carbon? Now that carbon has a double bond to it. It has a single bond to that sp3 carbon. And then what's not shown on that carbon is that there is a hydrogen here. Unless carbon has a charge, positive or negative, if you don't see another atom attached to it, it's understood to be hydrogen. All right, so that's we're going to talk about that when we look at the skeletal forms and Lewis forms in a second. All right, so and it's always going to have 4 bonds unless it's charged. If it's charged, then it'll have less bond. It'll have 3 bonds and either a plus charge or a minus charge. All right, so what is the hybridization state of that carbon, the red one? I heard somebody whispering it, I think.
SP2.
It's sp2. Very good.
Can you explain how?
Yep. We can explain it 2 ways, right? We can say how many groups are around it. Is that right?
Yeah.
Or we can say that it has a pi bond to it. 1 pi bond, not 2, right? So here, this carbon has, let's look at the groups. Let me get another pen. Let's look at the groups that are around it. Because remember, when we said something is sp2 hybridized, we said that it has a trigonal geometry and 3 groups around it. So 1 group is here, 1 group is here, and another carbon over here makes the 3rd group. So that's one way we can tell it's sp2. The other way is the fact that it has a double bond. All right, because sp2 hybridized atoms have 1 pi bond.
And the groups also doesn't the double bond also have to do with the groups? Since it is a double bond, there's not another like extension, like another something bonded to it. So there's not a separate group. That double bond is just considered one group.
Yeah, you can think about it that way. Yes.
Okay.
Yeah, that's a great analysis. You can think about it that way. So, and the reason you can is because the double bond is actually 2 bonds, right? And carbon is only going to make 4. So you got 2 bonds taken up with the double bond, and then on that particular carbon that's in red, the other 2 groups bound to it are just going to be there, right? You got 2 groups bound to it, and then the double bond takes up the other 2 potential bonds. So there's only going to be 1 other group on the other side. That's a good way to think about that. All right, but for, I don't know who that was that asked about how we knew it was sp2, but did that answer your question?
Yes, it did.
Okay, great.
Can you explain the blue carbon?
Yeah, so that blue carbon is sp3 because a couple of ways. We can do that 2 ways. We can look at the number of groups around it, right? I gotta erase that. We can look at the groups. We just said that there were 2 hydrogens. We just don't see them because it's written in skeletal form, right? So those are groups. That's a group. That's a group. And then it's got a carbon on this side of it and a carbon on that side of it. So it's got 4 groups around it. But the other way that you can tell it's sp3 is that there are no pi bonds, right? It's all sigma bonds.
How can you tell there's no pi bonds?
Because a carbon with a pi bond is either gonna have a double bond to it, or it's gonna have a triple bond to
Thank you.
it. That's a good question.
I have a question.
Go ahead.
Did you upload the notes from last class on Blackboard?
Yes.
Okay.
I try to upload them like as soon as class is over, because my schedule is always so hectic. I know I'll get sidetracked if I don't. So yeah, I usually upload them within an hour of class being over. All right, so that's that. So now let's go back and answer the question. What type of overlap is happening between, let me erase all this stuff. Or should I keep it?
Is it SP3, SP2
Very
overlap?
good. Yes, you're absolutely right. It's sp3, sp2 overlap between these 2 carbons right here.
Does it matter which order we put those in?
Nope.
All right.
And then let's take the double bond. Let's look at that. Right, and it's those 2 carbons. I gotta erase these circles. What do you think? What's the hybridization state of both of those carbons, since they're both participating in that double bond?
Is it SP2, SP2?
Yes, so that both carbons in that double bond are sp2 hybridized. So that's going to be sp2, sp2 overlap. Good. All right. What about here? We know the H, the hydrogen is what? What type of orbital is that?
S orbital?
Just a s orbital, right? And we know that carbon in the double bond is sp2. So this is just going to be sp2 s overlap. Y'all following that? Anybody not following? Say something.
Can you explain why it's a S2S overlap?
For this one, the one we just did.
Yes.
Okay, so the atom, the carbon in the double bond is here and it's bonded to this hydrogen. You following?
Yes.
And so that carbon is, we're gonna say it's sp2 hybridized because it has 3 groups around it and it has 1 pi bond. So we know that that's a characteristic of a sp2 hybridized carbon. Do you agree?
Yes.
Okay, and then the hydrogen is a simple s orbital, right? If you think about the electron configuration for hydrogen, it's just one s1. So it's not a hybrid. It can't add or mix or anything. It can bond, but it can't hybridize. So up here, when we say that, and let me ask this question: every covalent bond is a result of what? What phenomenon? That's the first thing I asked at the very beginning of class.
Orbital overlap.
Orbital overlap. So in order for that H to bond with that carbon, the s orbital on the hydrogen has to overlap with one of the sp2 orbitals on carbon. So that's why we say that it's sp2s overlap.
Okay, thank you.
All right, let's look at this one. I want to add in the oxygen too, but we can look at that. That's a good one. All right. What about this bond right here? What's the hybridization state of carbon? You can see it clearly that it has 3 groups around it. Yeah. It's got an oxygen, it's got a carbon on that side. It's trigonal. You see the triangle? Right. So it's trigonal geometry. So what do you think?
SP2.
The carbon is sp2. Very good. What about the oxygen? Oxygen has 2 lone pairs, but remember, those lone pairs are not like Velcro stuck to the side of the atom. That's just how we draw them. They actually sit in an orbital, both of them. And lone pairs are groups. Is that right?
Yes.
So
So-
how many groups are around oxygen?
3.
3 groups. So what do you think?
SP.
Go ahead.
SP2.
Oxygen is also sp2. Right? It fits the characteristic. It has a pi bond to it, and it has 3 groups around it. It has trigonal geometry. So it's also sp2. So that bond between carbon and oxygen in this case is sp2 overlap. All right, let's do this one real quick. What about that bond? What's the carbon at the vertex right here? What's the hybridization state?
SP3.
It's sp3. So we already know what this carbon is. So what type of overlap is happening to make that sigma bond?
SP3, SP2 overlap.
Good. All right. Are y'all following? Everybody good so far?
Can you explain that one?
The one we just did?
Mm-hmm.
Yeah, so the terminal carbon right here is sp3. Right? It's got 2 hydrogens on it. So 4 groups, no pi bonds, all sigma bonds. So that's sp3. And then we already established the one here as being sp2. So the bond between them has to be the result of one of the sp3 orbitals on that carbon overlapping with one of the sp2 orbitals on the other carbon.
I have a question. How do we know that it's all sigma bonds?
You mean on the sp3 carbon?
Yes.
Yeah, because like, okay, so here's let me go back. So here's a carbon that has all sigma bonds, right? Notice there are no double bonds or triple bonds. That's the difference. So if I have a carbon like this, it has a double bond to it and then 2 sigma bonds, or 3 because the double bond is made up of a sigma and a pi. Right? But unless you see a multiple bond, like a triple bond or a double bond, it's assumed that all those bonds are sigma bonds.
Okay, thank you.
Mhm. All right, let's see if we can run through this one real quick. And we're gonna, so you got the nitrogen, carbon, sigma bond. Somebody help me out with that one. Look at the nitrogen and tell me what the hybridization state is. Let me put the lone pair in too, so you know, that might help you. What's the hybridization state of the CH3?
The nitrogen have a SP2.
Good. And then this is what?
SP3.
Mhm. So we know that bond between them is what overlap? What type of overlap?
SP3, SP2 overlap.
Yes. What about here? What you're looking at is the carbon on the left and the carbon on the right. So this carbon and this carbon. What is the hybridization state of this carbon?
The SP.
It's SP. Good. Has a triple bond to it. Anytime you see carbon with a triple bond, it's going to be SP hybridized. And then this one over here on the right, what do you think?
SP2.
It's SP2. So the bond between them is what? SP, SP2 overlap. Is that right?
Yes.
Mhm. So let's look at the triple bond. This one is not as bad as it looks. So you got carbon, carbon, they have a triple bond between them. So we can look at the triple bond again as being made up, if you recall from the other day, 1 sigma and 2 pi's. Is that right?
Yes.
So for the, let's just look at the sigma bond. And for me, I always just pick the bond in the middle as the sigma bond and the other 2 bonds as the pi bond, but that's arbitrary. All right, but we're gonna, for the sake of the class, we'll do that. So what is the sigma bond between those 2 carbons the result of? What type of overlap?
And S overlap.
Say that again.
And S overlap.
Between the 2 carbons,
Oh, no.
both carbons are SP hybridized, right? If we say the one on the right is the purple one is SP hybridized, the other one in the triple bond also has to have the same hybridization state. So they're both SP. So the overlap between them is SP-SP. Is that right?
Yes.
Mhm. Now, where do we get the pi bonds from? Anybody recall?
From double and triple bonds.
Okay. So a triple bond does have 2 pi bonds. A double bond has 1 pi bond and 1 sigma bond. Triple has 2 pi and 1 sigma. But what causes the pi bond? Like what?
Unhybridized.
Yeah, p orbital overlap, right? Unhybridized p orbital overlap. Yes, I see your answer, Mary. Thank you. Unhybridized p orbital overlap. So anytime you have a pi bond, it's the result of 2 unhybridized p orbitals sharing electrons and forming a pi bond. All right. What about the last one? We should be able to spit this one out pretty quick. So you got a hydrogen here and it's bonded to a S. We already said that carbon was SP hybridized.
SPS overlap.
Yes, good, very good. So this is S and the other carbon is SP, so it's SPS or SSP overlap. Great, perfect. All right, let's see if we can do, actually I want you to do this one on your own, just to see if you got the hang of it. So I'm gonna put this here. So when you see that in the notes, OYO on your own, you need to do this question before you turn this, before you turn in the handout. All right, you think you can handle it? I think so. Y'all are smart. This is a good class.
You want us to do it right now?
No,
Oh.
I would put you in a breakout group, but we got to see how that goes first. I tried that last semester and I would go into the groups and everybody would be on mute. Nobody would be talking. So we got to figure out a better way to do that. But you can do it today, do it after class, whatever. Just make sure you do it before you turn the handout in. I think you ready to do it right now. I can hear it though.
I think somebody asked,
Go ahead.
I think somebody asked this question earlier, but you said that all the highlighted ones, we need to do those before we turn them in as well.
No. The
Okay.
highlighted questions, we're doing selected problems.
Okay.
And the only ones that you'll turn in are the ones that we do. But if I give you an assignment like this one and say, do this on your own, then you have to do that one as well.
Okay, thank you.
Yeah. All right, let's go back up to the top of this handout. I'm gonna pull a couple of these, problems so we can work through them. Because this is also a really crucial skill to have, is to be able to kind of work through the different structures. Because on the exams, most of the exam material is in skeletal form. So I want to talk to you about that real quick. Put another page here. Right, so when you're talking about carbon, and when you're talking about expressing carbon or drawing it as a structure, drawing it within a structure, you can express it a couple of different ways. You can write it in what's called a Lewis form. So we write out, let's just say, a carbon here with four hydrogens attached to it, which is methane, by the way. I know this was in one of the videos. It gave you up to the first 10 carbon, like 1 through 10 carbon chains. Anybody remember that?
Yes.
Okay. So this is methane. You can also write this like this, right? This is what we call the Lewis form, where you write out all the bonds. I can get my handwriting together. And then this is what we call the condensed form. Right, that's the condensed form, where you don't show the bonds, right? You basically show the atoms without showing the bonds. All right, so we're going to work through several of these examples, just going back and forth between skeletal and condensed and drawing, and we're going to work through the ones with different atoms so you can just see kind of how this works. So we'll take the last 12 minutes of this class and do that. So let's look at A, where it says convert each molecule into a skeletal structure. Now it's important to understand, like with A, what you have shown in A is the condensed form. This is condensed. See how all the carbons are shown with the hydrogens, just with the simple subscript next to them, right? So what we're going to do is expand this example. We're going to do both the Lewis, and then we're going to convert it into the skeletal form. All right, so let's do that. So let's do the Lewis form. And if you notice here at the termini, you have a CH3. You have a CH3 here with a subscript 2, right? And that's connected to that CH that's to the right of it. And then over here, you have the same thing, a CH3 with a subscript 2 connected to the CH that's to the left of it. So the middle part, let's focus on that first, and then we'll go back to the termini. So let's do that. So that's going to be carbon, carbons, 4 carbons, and then on each end, is a CH3. Right, or two CH3s, right? And then this is a CH. And then this is a C.
Are CH3 and H3C the same thing?
Yes, it's just a convention. Normally if the carbon is left facing, then you'll write it, because the thing is, if I wrote it like this, then it would look like it's the hydrogen that's attached, and it's not. Right, it's because the hydrogen can only be bound to one atom. So it's not going to be bound to a carbon down here and then the carbon to the left of it. You understand what I'm saying? So it's just a convention for clarity, to make sure you understand that it's carbon that's bound to that chain and not the hydrogen that's on that carbon. Right, and then does that answer your question?
Yes, thank you.
And even with that, these carbons, I drew them condensed, but you can also write those out as well, right? Because there's 3 hydrogens attached.
Dr. Russell, I remember something in the video, I guess it talked about how I guess the terminal end will always have a certain amount of hydrogens. And
Yes, every terminus is going to be a CH3.
Okay.
You'll see that when we do the skeletal form for this. That'll make sense. Go ahead, Tia.
I forgot what the video said, but how do you write it when there's an atom other than hydrogen?
You just write it out. We'll do B, and it has a chlorine and a oxygen in it. So we'll do that. Because that'll give me a chance to explain like the condensed form too and what it means. Because sometimes if you look at the condensed form, you really don't know which atoms are bonded to which. So it'll give me a chance to explain that too.
Okay.
All right, so that's the line, the Lewis form. And then this has hydrogen on it too. Right now, if I wanted to write the skeletal form for that, well, I can do this a couple of ways, but I'm going to show you the proper way. So let's just do that. We're going to find the longest continuous chain. 3, 4, 5. Looks like 6 carbons. Do y'all see that?
Are we still on A or is this B now?
No, we're still doing A.
Okay.
So we have the condensed form. We drew it out as the Lewis form. And then can you see that the longest chain from one end to the other, it follows the path of those yellow carbons. The 6 carbons. Is that right?
Yes.
And I know that somebody's thinking this, well, couldn't I do this instead? And the answer is yes. I can count from here like that. Or I can start counting from the other end. It doesn't matter, but the longest chain is going to be 6 carbons. Are y'all following?
Yes.
Yes.
All right. So if I wanted, if this is my Lewis form, I should have put this on a blank page. And then my skeletal form is going to look like, now with the skeletal form, your terminus, you can start here or you can start here, it doesn't matter. But I like to start here. So that's 6 carbons. 1, 2, 3, 4, 5, 6. 1 too many. Come on, Russell. Right, that's what the skeletal form is going to look like. It's skeletal in that you don't have to show the hydrogens or the carbons, right? You only show the vertices, right? Each vertex, 1, 2, 3, 4. That's those 4 carbons in the middle. And then the terminus will be the 2 end carbons right here and right here, right? Those are your termini. All right. And then if you look back at the Lewis form, on that second carbon, there's another CH3. So I need to write that in. Right here. And it's the same thing on carbon 5, which is on the other end. I need to write in another CH3.
Why do you have to write in another CH3?
If I just left the chain, do you see like right here? So when we picked out, let me see if I can sketch this out. When we picked out the longest chain, do you see that?
Yes.
You see the other carbons attached to it? Right here and right here.
Mm-hmm.
We can't leave them out. Otherwise, it's a totally different molecule. If we just do the 6 carbons, it's hexane. But we
Right.
have to add those other 2 groups in because they're in the original structure.
Okay. Doesn't
Great
matter-
question.
Doesn't matter where you put them?
Yes, you have to put them where they are in the original structure. So like right here, this is 1, 2. Let me change colors up there. This will be 1 through 6. 1, 2, 3, 4, 5, 6.
Oh,
So you see how this is bonded to carbon 5 right here,
right,
and this is bonded to carbon 2 right here.
right.
Yeah, so I got to put them in the exact same spot when I draw the skeletal form out. I
Okay.
really should have put this on a blank page. I didn't realize it was going to take up so much space, but that's okay. I'll move it before I post the note so it won't look so sloppy. All right, so that's my skeletal form. In the skeletal form, again, every vertex, and these are vertices right here. That's a vertex, that's a vertex, so is that, and so is that. Every vertex is a CH2 unless there's another atom attached to it. So like right here, where that other methyl, the other CH3 group is, there's a hydrogen, there's only one hydrogen there because it already has 3 bonds to it. The same thing on the other end. Right, just like up here, you see how it's different color pen. Right here, you see how it's CH. So down here, it's going to be the same thing. That carbon is going to have 1 hydrogen to it. And we're going to work through some more of these because I know this is like it's kind of jarring to go from hybridization back to this, but I want us to have a good foundation because I want you to be able to distinguish between these different forms. All right, so Lewis form versus condensed versus skeletal. Let's take, let me move this. Let me move all of this stuff. Put it on a blank page. Uh-oh. This is sloppy. It looks sloppy laid over top of that like that. Okay, perfect. I'm gonna put it down here.
I have a question.
Go ahead.
When do we turn in this assignment?
The day after the test.
Okay.
Let me copy the one we were working on. Then we're gonna try. Oh, we're not gonna be able to squeeze it in. I don't think. What do you think? You think we can squeeze one more in? I think. Because I want to look at B because B is a great question. It's like a bunch of different concepts all rolled into one question. But I'll wait. We'll do it on Monday. On Monday, we're gonna kind of finish up on this and the formal charges and the structures, and then we're gonna jump into resonance and polar covalent bonds and dipoles and all that stuff. So make sure you watch the videos that I sent from 1A. Did I send that already? Dealing with resonance?
No, and the last time you sent the email, you put what videos to watch, but there were no links underneath.
Really? I feel so ashamed. I'll go back and make sure that I edit that because it should have been videos from 1A, but I'll take care of it.
I noticed.
Go ahead.
whenever- I noticed like, cause she said like the email, I noticed on the email that too, it didn't show any videos, but then if you go back into announcements,
Mm-hmm.
it doesn't have a link to the video, it just has like the actual video.
It has a thumbnail, right?
Yeah, it's like it showed up in the announcement, but didn't like convert over to the email.
Yeah. Sometimes Outlook will do that. Like it won't bring all the links and the information over. And then in Blackboard, I noticed that when I started posting the links, it won't put the link, it'll just put a thumbnail that you can click. So what you could do in the Blackboard announcement is just right click on it and just open the video in a new window, and that should solve it. But I'll make sure that the links are there also.
I have a question too. I don't get none of your emails.
Really?
No.
Are you using Outlook?
Yes. Like I get emails regularly. I just don't get any from you.
That's weird. So all the announcements, you don't get any of the announcements from Blackboard?
I just check Blackboard, but I don't get like, if you're talking like Outlook emails.
Check
No.
in your, because you know Outlook has like a focused inbox, and then it's got another inbox
Mhm.
for everything else. Check and see if your inbox is kind of separated like that.
Okay, because I know I'll be asking a lot of questions in this group chat, but it's really because like I just want to make sure like I'm on point. So
Yeah. Well, you should ask questions now. Don't ever not ask questions. That's a good thing.
okay.
But yeah, check and see if your inbox is split, because I know mine is. It's split between focused, and then everything else goes to a separate inbox.
Okay.
It's not spam, it's not junk mail, it's just a separate inbox.
Okay. I'm gonna
Yeah.
check. Thank you.
Check that out.
Can you clarify what questions we're supposed to be doing for homework?
So the ones that we're working in class, those are the ones that are due for now. And then I also assigned another question for you to do on your own, which was this one, 171. Like we're not doing each and every question from each and every example from each and every question. We're working through selected examples in class. And unless I specifically say, do this on your own, then whatever we do in class is what you're going to turn in.
And this is on Blackboard. I'm sorry.
Say that again.
It's on Blackboard.
This handout?
Mm-hmm.
Yes.
Okay. I'm still trying to, because my Blackboard is like different. So I'm still trying to learn how to navigate it, and it be shutting down on me. I don't know if it do that to anybody else, but like it be sending me like error. So this is under assignments, or is under 1A mod, like the
Yeah,
mod.
it's in module 1, actually.
Okay. All right.
It
Thank
says
you.
first module, and